This video was produced as a study guide for students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. The discussion will be on slow-speed diesel engine fuel oil injection systems. The reading assignment for the material that's covered in this presentation comes out of Pounders, Chapter 8 on fuel injection, and Chapter 10 on the Burmeister-Wain low-speed engines. For those interested in delving a little bit deeper into the variable injection timing, we have also on Moodle a service bulletin on the adjustment of the variable injection timing. This presentation is an overview of the Burmeister-Wain high-pressure fuel pump consistent with the Kongsberg MC90 simulation software. The lecture begins with a review of material already covered by the EPO 220 Diesel Engineering 1 course. It will expand the discussion concerning the more advanced features of the Burmeister-Wain pump. At the end of this lecture, the student should have a better understanding of the important design features of the Burmeister-Wain high-pressure fuel pumps. We will discuss basic port and helix fuel pump design features, variable injection timing, the puncture valve, suction valve, fuel oil recirculation, the shock absorber, and for engine reversal, how it shifts the follower angle. So this is an illustration of a standard port and helix pump that is used on multiple engines, including both the Enterprise main propulsion on the training vessel and also on its auxiliary diesel generators. One thing about the pump that we'll talk about briefly is you have the pump barrel and the pump plunger. On these high pressure pumps, injection pressures today are pretty typical between 1,000 and 2,000 bar. A bar is 1 atmosphere or 14.7 psi. So you're basically talking somewhere around, on average, about 25,000 psi injection pressures. There is no sealing rings on this. Specifically, leakage is controlled by the tight fit between the pump plunger and the pump barrel. These cannot be replaced separately. The clearances are so tight that they have to be installed and removed as a unit. So when you're looking at clearances on this, when you're talking about of distillate fuels, you're looking at about 7 to 9 microns. A micron is a millionth of a meter. So you're talking very, very, very tight tolerances. Now, there will always be some leakage down the plunger, and it will drip from the bottom of that assembly because you have to have fuel to lubricate the plunger and barrel. They're metal, sliding metal to metal surfaces. They have to be lubricated, and they're lubricated by the fuel. Now, on this pump, in the lower part, you'll see the grooves along the lower part of the barrel. And there's another groove that intersects the two horizontal. And that is there to collect a small amount of the fuel to make a reservoir for the lubrication. Now, on some high sulfur residual fuel engines, they will also supply a small amount of lube oil in that area to help lubricate. The other one here, on either side of your spill and suction ports, you'll see there's it's some called like a wasting plug. When that fuel comes out of that barrel at the end of injection, it comes out at very, very high speeds. And it can be some erosion of the housing. To prevent that, what they do is they put in a very erosion resistant steel, and those plugs are replaceable if they were to become eroded over the life of this pump. Now, another thing I want to mention on this is that with this type of pump, start of injection is always the same. End of the injection varies, and that end of injection is controlled by rotating the pump plunger, and that helix, when the helix uncovers the spill port, you have end of injection. So you're rotating the pump plunger to control the duration of injection. But these pumps, the start of injection is always the same, and the start of injection is when the pump plunger covers the spill ports. Once that happens, then injection will begin, and injection will continue at a continuous rate until, as the pump plunger rises up and the helix uncovers those spill ports, then the fuel will, instead of being delivered to the injector, will go back into the suction of the pump. So one of the things that needs to be discussed is that you're taking, and this 25,000 psi, right, or 1,500 bar fuel is being dumped back into the suction line. So you have a suction line that is supplying fuel to the pump at typically about 8 bar. All of a sudden you're dumping 1,000 bar fuel into that suction line, and that can cause pressure pulsations in the suction line. The other one, another point to mention within the discussion is when you look at the pump plunger, you'll notice that the pump plunger has to rise a certain amount before it closes the spill ports. And that's intentional, and that is an advantage to this pump, because what happens is I want that pump plunger to send a shock wave to the injector. You don't want to think this so much as pushing fuel as but sending a shock wave. That shock wave will hit the injector needle valve and snap it open very, very quickly, and that's what you want. So you want to accelerate that pump plunger as quickly as possible, and you want it to be accelerating strongly before the ports close, and then that will give you a good shock wave for that instantaneous opening of the injector. And that's very, very important to prevent particulates. You want a high pressure flow out of the injector nozzle to give you better atomization. Now, on these port and helix pumps, you typically have a delivery valve at the top of the pump. That delivery valve is there to keep the high pressure pipe full of oil. Otherwise, once injection has occurred and the pump plunger is moving downward, that is going to draw a vacuum or lower pressure above the pump plunger, and that would lower the pressure in the high pressure pipe. That would be a disadvantage because that would impede that shock wave hitting the injector on the next injection stroke. So they put a delivery valve so when the high pressure line, the pressure in that line is higher than in the space above the pump plunger, then the check valve will close and prevent that line from draining back. Also, long high pressure pipes are disadvantageous with fuel injection. You want as small a high pressure pipe as you can, again, to help propagate that shock wave and prevent shock waves from moving back and forth between the injector and the delivery valve when injection ends. And then you have a control rack, and that control rack rotates the control sleeve, and there's a flange on the pump plunger, and when the control sleeve turns, that rotates that plunger back and forth. You have the land on the plunger, and then you have the helix underneath it. The wider that land, the longer the duration of fuel injection. On the Burmeister-Wain pump, the pump itself is, or excuse me, on the Burmeister-Wain engine, the pump is located quite high on the engine side. And they do this by using a chain drive to drive the camshaft. Now, when you look at this drawing and you look at the camshaft lobe, realize that's not the fuel pump camshaft lobe. That is for the actually exhaust valve. But these high pressure pumps are located quite high on the engine side, and they do have pressure pipes, and they have actually two injectors. So each pump has two high pressure pipes coming off of it. But in relation to the size of the pump, the high pressure pipes are quite short, because the Burmeister-Wain is the only separate pump and injector system that I've seen that does not have a delivery valve. And I've talked to Burmeister-Wain, some of their representative about this, and the basic gist of what I received back is that since the pump is so large and the pipe is so short, that these act more like a unit injector, and that the delivery valve was not a very high necessity for this pump. And we're going to talk about it in a little bit coming down the line, that instead of a delivery valve, these engines have a suction valve at the top of the chamber formed by the barrel and the plunger. So this is a picture of the Burmeister-Wain high pressure fuel pump, and you can see coming off the top you have two high pressure lines, and the one on the right you can actually see where it comes down, and then you can see the injector itself. And this is the high pressure Burmeister-Wain fuel pump. One of the features we're going to talk about first is variable injection timing. Variable injection timing is very, very significant and very important for engines running on heavy residual fuels. Now, if you're talking about an engine such as used on the roadways in the United States that's burning a clean distillate, and specifically what we would call in the marine industry marine gas oil, what shoreside is known as number 2 diesel, the ignition delay for those fuels is a standard, and it will not change. It's about 10 milliseconds. So in other words, when you inject fuel into the cylinder, it will atomize and then ignite in about 10 milliseconds. Heavy residual fuels, depending on the fuel quality, that can vary drastically, and that will change the timing of the engine. So for heavy fuel oil engines, it's very important that you can change the timing of injection depending upon the ignition quality and the ignition delay of the fuel that you're burning. Now, this is an illustration of a modern electronic indicator card. The newest engines, this information is available to you online all the time. And every time you change over to a new bunkers and you're burning a new bunkers, you will need to take an indicator card at least on one cylinder so that you can see if there's a timing change because of that ignition quality. And if there is, then what you would do is you would change the injection to give you a proper indicator card. Now this one is actually for a 4-stroke engine, and ignition occurs right before top dead center. On a slow-speed crosshead engine, the injection or ignition of the fuel will occur at least about 3 degrees after top dead center. So for on a slow speed, it would occur after this curve just starts heading down. Now the other thing we'll talk about too, there's other reasons to have variable injection timing, and we'll get to a second. But let's look at a standard Burmeister-Wain card. So, normal injection, this is showing here where ignition would occur, and this is late injection. Now, what's happened with this is the fuel is burning maybe 6 or 8 degrees after top dead center. When that occurs, that piston is accelerating downwards, and the volume is changing rapidly and increasing rapidly. So when you inject it late, the volume is quite large, and you will get a significant drop in the Pmax pressures. And ignition occurs down here instead of where it was supposed to, which is right over here. Now, advanced ignition, you get a much different card. You can see on this where ignition occurred prior to top dead center, and I will get a very high Pmax peak, a fairly dramatic rise in the Pmax. That's because as the piston is moving up, your volume is rapidly decreasing. So when that fuel burns, you've got a very, very small space that it's burning in. So or clearance volume is the proper term that I should be using. So advanced ignition will give you a pressure spike and raise Pmax fairly dramatically. Now, this is a indicator card with an engine that has retarded ignition due to low fuel quality. And you know it's low fuel quality because when you go down the engine and you look at each one of the cylinders, all of the cylinders show this same problem. So in this, that the ignition is occurring at about 15 degrees after top dead center, and it should be occurring about 3 degrees after top dead center. This is just a close-up at the top and near the peak, and you can see where your compression pressures came up to a maximum at top dead center, and the volume's starting to get bigger, the pressure's going down, and then ignition occurs. That's a fairly indicative of a slow-speed crosshead engine that has retarded ignition due to fuel quality. All right, this is a cutaway of a Burmeister-Wain high-pressure fuel pump. The features that have been added to this pump are the puncture valve, the suction valve, and variable injection timing. And we're going to talk about variable injection timing first. And one of the things that is very recognizable on this is that you have 2 racks. The lower rack will rotate the control sleeve to change the position of the helix and vary end of injection, or the amount of fuel delivery. The upper rack is variable injection timing. Now, if you look closely down at the base of the barrel, you'll see that the bottom of the barrel is threaded, and it goes into a threaded connection. So when you rotate using the rack, when you rotate that, you will actually be threading that barrel in or out. Well, when you thread that barrel down into that thread, it's going to drop, or the opposite, it's going to rise. The amount that it is if you look at on the side of the barrel, there's a stud that goes into a slot in the barrel, and when you look at that, you can see how long that slot is. That gives you a fairly good indicator of how far that barrel can move up and down. So I want you to think about this. If I lower the barrel, what's going to happen is as the camshaft is turning, the land of the plunger will cover the spill port sooner. If I raise it, that camshaft lobe is going to have to keep traveling. It's going to have to travel more. before it raises the pump plunger up high enough to cover the spill port. So you're changing injection timing for raising and lowering the barrel. And it can raise within that housing. The other thing I want to mention at this time is there's not separate spill and suction ports on that barrel. They basically both act as suction or both act as spill depending on where the cycle you are in. The incoming fuel is going to be around the entire outside of that barrel. Now, what you're seeing at the top of this is the puncture valve. The puncture valve gives the manufacturer the ability to disable each of the fuel pumps, high pressure fuel pumps, with a pneumatic air signal. And this is very important. There are different times that one of them would be an emergency shutdown. When you have an emergency shutdown, an air signal works upon this plunger at the top of the pump. And when that plunger moves down, there's a check valve directly underneath it, and that pump plunger will open that check valve, and which opens the pump cavity back into the suction. So in other words, if active delivery is ongoing, no matter where the port helix is, right, that puncture valve opening up that check, what will happen is the contents of the barrel will spill right back to the suction, end of delivery. Now, this is used for emergency shutdown, but where it's also used is at the start of each time the engine goes to start. While you're injecting air into the cylinder, that puncture valve is activated so that you have no fuel delivery until the engine rotation comes up, and then what happens is that signal goes away, the puncture valve closes, fuel injection starts, and then immediately afterwards the start air is secured. Now, if you look above the pump, at the top of the pump barrel, you'll look at and see another valve. That's the suction valve, and we'll talk about that a little bit later on. But what the suction valve does, it allows for recirculation through these high pressure pumps when the engine is shut down. So on the variable injection timing, there's a little bit better drawing here, and you can see on the bottom of that barrel that very aggressive thread, and then your control sleeve, right? So that control sleeve threads onto the bottom of the barrel, and then you have a pneumatic piston that moves the rack back and forth to rotate or lower that pump barrel. And this is tied into also the governor. So that governor, not only fuel quality, but depending upon engine speed, as the governor increases fuel delivery, it will also adjust your injection timing, and we'll talk about why in just a second. All right. Engines will raise up to Pmax at 100% load. And when you look at this drawing, you're looking at the green line on the bottom, that's scavenging pressure. Now that's one of the things to think about, is that your compression pressures will increase as the load on the engine increases. And I want you to think about that. There's a good reason for it. Your turbocharger is spooling up. As the engine load increases, your turbochargers are going to spool up, are going to put more air, scavenging air into this engine, and they're going to raise up both your scavenging and your compression pressures. So blue is your compression pressure, and then when you look at the red, that is your Pmax, the maximum pressure obtained in that cylinder during the cycle. Now, if you had no variable injection timing, it would rise up to 100% along that dotted line. So you wouldn't get maximum, the Pmax, until 100% load. Well, what they found is that those high pressures and temperatures at Pmax help with fuel combustion, and you get a better burn at Pmax, at the maximum pressure when at 100% load. Well, you don't run an engine typically at 100% load. You run it about 85 to 90% typically. So by increasing to Pmax at 85% load, you're getting a better burn and better fuel economy. So the main thing on this, you get better fuel economy by changing your timing. So when you look at this, you've got a lower break point and an upper break point. Typically on the Burmeister Wain, you start advancing the timing after 45% load so that you are at Pmax at 85% load. And then you've got to take and start retarding the timing back so that the Pmax flattens out and doesn't, and so you'll basically have the same Pmax if you go up to 100% load, and it's the same Pmax from 85 to 100, which is the range that you normally run in, and that gives you better fuel economy. So to do this, that pneumatic piston has a that moves the rack back and forth, has a pneumatic signal going to it that is going to increase from 45% to 85% load, rotating rotating the collar, and then your barrel will actually lower down, and by lowering down, then that is going to advance your timing up to 85% load. After 85% load, your pneumatic variable injection timing signal will decrease and the barrel will move up to retard the timing so that you've got Pmax is fairly flat from 85 to 100% load. All right. So your variable injection timing is going to change about 5 to 6 degrees. You're going to, from 45% load to 85% load, you're going to say advance your timing about 5 degrees, and then from 85 to 100%, you're going to retard your timing about 5 degrees. Now, when you look at this screen, what you are seeing both in a photo and over to the right on a diagram is how this pneumatic signal is changed as the governor changes position up, and how you set that lower break point and the upper break point. And it's done mechanically. Now, what you're seeing is you have a little pneumatic air regulator, and it has a pin that sticks out from the front of it. And then you have a bar that's going that goes up vertically. You've got this bar, and you've got a spring pulling it to the right. And then you have 2 pins, these pivot pins. So if you look to your right, as that governor moves forward, that bar is going to pivot off the upper pin, and then it is going to start pushing at about 5 to 45% load on that air regulator, and it's going to change the air output going to the pneumatic actuator. As that regulating, or excuse me, as that the fuel regulating shaft is what they're calling, but the governor arm moves, at some point the bar is going to hit that lower pivot pin, and then what ends up happening, the bar rotation is opposite. The top will start to move left because you're pivoting off the lower, and then what that does is the bar moves away from the pneumatic control valve, excuse me, the pneumatic regulator, and your air pressure then will change back. And this is how you would adjust this, and this is how this mechanically that they are controlling this variable injection timing off the governor. So again, the 2 reasons that you will typically change, or why this mechanical system was installed, was to give better fuel efficiency between 85 and 95% load, and also to be able to give a better burn by changing the timing when you have fuel bunkers and the fuel quality changes. Now on the simulator itself, you can see that these are set up very similar to what we've been talking about. You'll see the puncture valve on the top. You'll actually see where there's two high pressure lines coming off the pump because these engines have two injectors. And then down below you'll see the two racks. The upper one is for where you can change your fuel injection timing. The lower rack is for fuel delivery. And then you have the variable injection timing, and you can do adjustments on that on the bottom. So again, on this you have the rack moves back and forth. You have a control sleeve, a threaded barrel, and that will move that barrel up to retard timing and down to advance the timing. All right, we will end this part of the discussion at this point. You will need to listen to the part 2 to finish this presentation. Thank you very much for your attention.